Okay, we're continuing on with our video session here about the homework. So we're on number, oops, I can't see that. We're on number 6. Continuing with the data from problem 3, if we retain two of the basis vectors, how much variance as a percentage is explained by this plane, or by the span of those? This refers to the discussion in the text about how to compute the rank. So let me pause this for a second and find that section in the text. Okay, I found the material here on page 63. If we scroll up, see that. Speaking of rank, okay, so we want to find, where is that? We had a relationship between the eigenvalues of the covariance and the singular values. Of course, we already have the eigenvalues of the covariance, so we already have the lambda i's here, and so lambda I hats, and so we're going to need to normalize those so that the lambda i's sum to 1. Okay, and then we want to keep enough dimensions r so that lambda I is greater than or equal to tau when you sum from 1 to r, but if you sum from 1 to r minus 1, it's less than tau. And so in that case, we would say, here it is, that it takes r dimensions to explain or encapsulate tau percentage of the variance in the data. So what did we say? How much variance is retained by keeping the first two eigenvalues or eigenvectors? And so that would be the sum of the first two normalized eigenvalues of the covariance matrix. So let's take a look at those again. Those are in D, so let me put those in a diagonal matrix vector, diag D. Okay, so those are our three eigenvalues. Notice they are in the wrong order. So I could reorder. Oh, let's go ahead and reorder. Let me. Let's see. So that would be n to 1 equals ss. However you want to do it. Oops, what did I just do? Did I just wipe them out? Oh, that's weird. I thought I could do that. Well, I could just take ss. Oh, now I remember what I did. I need to do n by minus 1 by 1. Oh, I already deleted them, didn't I? God, I feel like I'm Homer Simpson here. Let's see, try this again. Or did you guys see that where he was typing on the computer with his nuclear power plant? Okay, ss equals ss 3 by minus 1. What is this? Okay, there we go. Now they're in order. And so now we want to normalize those. So how do I normalize? I'll take divided by the sum of the numbers. Okay, and so if you sum the first two, you see that we're going to get 96%, 967% of the variance. So that's what you would say. By the way, there is a command for that, cumulative sum. I should have saved that as something. And so the sum of so this is the partial sums. So the first element is the first sum, and the second one is the sum of the first two, and the third one is the sum of the first three. So you can see that we'll be saving, oh gosh, I answered the question for you. 96.7% of the variance is explained by the first two. Okay, now what? Let's go to the homework again. We're on number 7 now. Load the clown data. We obtain a matrix that is 200 by 320. Treat this as 320 vectors in 200. Double center the matrix. Plot the best two-dimensional basis. Project the dimensions. Okay, you know what? I think I'm going to do number 7 by hand. So I don't solve the problem for you. Because actually we know all the pieces now for number 7, don't we? I think so. So I think I'll do number 7 as a separate video, although well, gosh, I guess it's here. Okay, You talked me into it. Load clown data. Remember, that's on our class website. Good. Now, what do I have here? X is my vector. Notice it's in n by p form, right? So we're thinking of the vectors as being in R200. So the best basis is also going to be in R200. And so the standard SVD is going to work. We want to double center the matrix first. So we'll take the column mean and the row mean. So let's do row mean, column mean, grand mean. It's going to be the mean of the mean. There's other ways to compute it, but that works. Those are our three means. So now we mean subtract. XM equals X minus row mean. It doesn't matter which order you do this in. But remember to add the grand mean back in. Okay. Oops. Now, be careful. If you don't use a semicolon, what's going to happen? That's going to happen. And you're going to run out of execution time. Okay. Oh gosh. Okay. 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 So that's a problem. Okay. But let's see. Did it actually compute our quantity? Maybe we shouldn't trust that. Let's go ahead and do that again, just to make sure. Put a semicolon on and you won't have a problem. There you go. Good. Now, SVD. Economy size SVD. Done. Now where's our basis vector? U. So what's the coordinates? Do you remember how to compute those? That's what you do, because we've already talked about that. And then you plot the coordinates. We've talked about that. And so finally you put in your reconstruction. I think we've talked about that too. And then you make the image out of your reconstruction. Good. So I don't want to answer all of the questions there. I think I've answered most of them though. You're very close to finishing. So I will talk to you later.